So thank you all for all your comments. They're super useful. And I want to emphasize, keep sending us comments. You know, the feedback really, really helps. But I do want to emphasize also comments directly in class. So for example, a couple of people wrote, please explain what you're doing, which is a great comment to hear, right? It tells me that it's not coming across. But of course, the problem is that in my head, I am explaining what I'm going through, right? So it's really helpful if during the lecture, instead of waiting for after lecture, you know, send in a comment that is really useful. But it's also helpful, perhaps even more helpful, if during the lecture you just raise your hand and just say, I didn't get that, right? So that I know that there are people that aren't getting it. Anyway, just to say that. All right, so somebody asked for us to go through how to do directories in Julia. The way to do that, so directories are the folders that you guys work with. Say if you're on a Mac, you're using folders and all your data or all your files are in a particular folder. And in Julia, and I don't think that this is in the file that I sent out. By the way, I should say I sent out two files, one called pre-written day 4 by email. So I only sent it out, I don't know, 20 minutes ago. So if you guys haven't checked your email recently, look at it, you'll find it there. And in there is everything that I'm going to do today. A lot of it I'm going to write from scratch again on the screen because I think it makes me go slower through it and explain it more if I write it as I go, rather than just show you the finish function. But the finish function is there and it's commented so that you guys don't have to copy it from the screen. Plus, we'll be posting the screen recording. So I think you guys might be able to just close all your laptops. And, I won't force you to do that, but I would recommend you to do that so that you're paying more attention to what's going on and asking more questions rather than focusing on just transcribing, which is not that useful. Okay. Oh, the one thing that isn't in that file that I sent out in the pre-written is the directory stuff. So if you're worried about that, maybe the next 2 minutes you do want to copy it down. So pwd is a function that tells you what the current directory is. So say in my particular case, this is the directory in which I'm working, and it returns it as a screen. And if you want to change directory, the function is one called cd, and you give it the string of the directory that you want to change into. If I want to change one level up, that is this dot dot. So if I do that, and now I ask what directory am I in, the answer is one level up from this subdirectory week 1. Now we're in the directory programming module. And if you want to see what's in that directory, you type read dir like this. It's that function. And that'll return a list of strings where each string is the name of a file or a directory in that directory. So say that I want to change back into my directory week 1, which is where I have all the files for today and for last week as well. And I'm going to do cd for change directory. I want to change directory into week 1. Now if I ask where we are, here we are back again. So hopefully that'll help you guys kind of like navigate through the directories. And for example, we could also have gone, you know, from the very root of the file system. So say I could ask to go all the way back to my home directory, or you can navigate around whichever way you want. Any questions about directories? Getting to the directory that you need to get to, seeing the files? Okay. Okay, so I'm going to say the main thing that I like to do, as I said, is this smoothing function because of its similarity to problem 2D. And I should say we chose problem 2D because it contains all the kind of key elements that we want you guys to learn, which is writing a function, for loops, if statements. If you guys can do that, then we're pretty good for moving on. But before that, I want to say a little bit more about vectors and types and creating things. So I told you last week about the command zeros, which makes a matrix of zeros. So for example, this means make a matrix of zeros and have it have 3 rows and 4 columns. And if I do that, here's my matrix with its 3 rows and 4 columns, and it fills it with zeros. We also talked about ones, and use that one too. But what if you don't want to create a matrix with rows and columns? What if you just want a vector, one of those vectors that is one-dimensional? It isn't really made up of rows or columns. Okay? In that case, you just pass one argument. So for example, zeros of 3, it isn't specifying both the number of rows and the number of columns. It's just giving me a length. And so it returns one of these items that, unlike this one, unlike when we called zeros of 3, 4, which had 2 dimensions, and you can see number of rows, number of columns, this one has only 1 dimension, and it has 3 elements. So that's how you can make a vector like this. Now, sometimes you want your vectors to be able to contain floating point numbers. So you want each shelf in that vector to be able to put a floating point number in it. And sometimes you want it to be an integer. When is it that you want it to be an integer? A typical case when you want it to be an integer is when you want the contents of that vector to be a pointer to an index into the number of the shelf in another vector. And we're going to do this in a second, and that's why I'm explaining this to you guys. So for example, say that we have a vector y, and we might have another vector, say v, b, y, and b. And we might want to put in here which of these elements of B we want to access. So for example, if we put in a 3, we might want to be able to call something like B of Y of 2. Like this, we access it, it's a 3, and that should point us to this element. For that to work, this has to be an integer, because shelves come in integer numbers. So if we want, you'll notice here our vector zeros is a 3-element vector of floats. So how do we make it be a vector of integers? The way you can declare that, you can make one of those, is by making the first argument, you tell it the type of thing that you want in there. So if I tell zeros, oh, I want you to be of this type, then it'll make a vector of integers. So let's say that we make a vector of integers like that, y equals zeros of int 64, 3. Okay. And let's say that we make the second one be equal to the integer 3. So how much is y now? Here's the 3. And let's say that we had another vector that is now b, and that is actually floating point numbers. So this vector b is 4 floating point numbers. Now I can ask, what is b of y of 2? Y of 2 is going to be this integer number 3. The third element of b is 7.8, so this should come out to 7.8. There's an error that can happen when you're doing this. And so I want to alert you guys to that. Suppose that we make our vector y, and we said this thing is going to be integers. Or we happen to have a vector that is set to be integers. And now we say y of 2, now we try to store a float in it, 3.6. Then we're going to get this type of error, inexact error. So if you see that error, probably what's happening is something like this. You're trying to store a floating point in a shelf that can only take integers, and Julia's saying, that's inexact. I don't know how to deal with that. So, yeah.
Can you explain to my, the second number, why the y would be, why the y2 would be the third spot?
Yeah. So if you're trying to kind of parse out something like this, try and think in sequential steps. So here it's written as one thing. Remember that the computer always goes in simple sequential steps. So having written that is equivalent to writing this. Let's write an intermediate variable. Let's just call it z. Let's call it z. And then asking for b of z. So what I mean is that when Julia encounters this, it says, I'm going to look inside the square brackets, and I'm going to try and evaluate that. I'm going to try and figure out what that is. And so that's what we're explicitly saying here. So what is y of 2? why, that is the same as saying, oh, give me the value of whatever is in the second element of y. That turns out to be the 3, so z is going to be 3, so this now becomes b of 3. Yeah?
Can you make an array of empty strings?
Can you make an array of empty strings? Yes, I think you can. I think the way to do that would be with this command, which looks different to the zeros. And you give it, say, the number of rows and the number of columns, and let's see what happens. They're undefined. I'm not sure. Okay. Another question that came up last week. So ignore this stuff. If that is confusing, ignore that one. We're mostly working with numbers. Another question that came up last week was about how to add, if we have a vector, say that we have a vector that has 4 elements in it. So let's do our favorite declaration. Let's say that they're going to be integers. By the way, we could also ask for floats, in which case the elements in the shelves will be able to take them in floats. But for now, let's say that we do our vector of integers. Now let's say that we wanted to grow it, that we wanted to add something to it. We wanted to append something to this vector. An append, the command I'm going to tell you now, is something that only works with vectors. It doesn't work with matrices. The reason it doesn't work with matrices is that if you have a matrix, say that you have a matrix that has 3 columns and 2 rows, if you ask to append a number to this, Julia doesn't know kind of where does it go. Do you want it over here? Do you want it here? Do you want it as another row? Whereas for a vector, it's very clear. It's one-dimensional. Appending, the meaning of appending is clear. So let's append something to y. I don't know, the value 10. And you write it like this with the exclamation mark. And I'm going to tell you guys again, I think after the directory stuff, I think I did put everything in this file pre-written. So all of this stuff is somewhere near the top. I believe it's in there. And in any case, it's in the recording. So I'm saying that to once again encourage you to stop copying and just close your laptops. I suspect that nobody's going to pay attention to that, but I'll say it anyway. Okay, so we have our vector y. It has 4 elements. Now we want to append something to it. So that means create an extra shelf and put some value in it. And so when we do that, now y, let me ask for y explicitly, now y instead of being length 4 is length 5, and that 5th one is that 10th element. Okay, so why am I saying? I'm saying that partly because last week we were looking at, when we were finding peaks, we were building a list, and one of the ways to build a list of peaks as we found them is to append the new peak to the list of peaks that we have so far. So we're going to come back to that. We're going to come back to append. I see a kind of furrowed, worried brow, and that worries me. Things clear so far? Any questions? You sure? Yes?
Can you append a vector to another vector?
You know what? I forget. Let's try it. And that reminds me to say, I want to point out that there's a lot of resources for Julia. I'm coming back to your question. I haven't forgotten. So say that you're doing a problem set or you're faced with something, you're trying something that hasn't been covered in lecture yet. Yes, our job is to cover it in lecture before you see it. But in addition, we really want to encourage you guys to explore and kind of try and find your own resources so that you can move faster. So on the wiki for the course, we just kind of re-highlighted this. So if you haven't seen it, it's because we just put it back up today. A link to the documentation. That can get very technical, but it's very complete. There's a wiki book which explains a lot of Julia things, kind of like in more detail. It's more for beginners. So if you see something that I didn't explain, try and see if it's there in the wiki book. We pointed you guys to this thing, Julia Box. This has a great set of tutorials. So again, if you're encountering something that hasn't been explained, you can look there. And finally, the most important one, and this is how I think a bunch of us have learned a lot of programming. You have a question? Google it. there's tons and tons of discussion forums that answer a lot of questions that you might have. So, for example, can append, oh, and the fifth one I should have put down. Don't be afraid of trying stuff. Can append a vector? I don't know. Let's just try it, right, and find out. So let's say we've got our vector y, and let's try and append a vector that's composed of two elements, 22, 23. Yes, it can. So now we know the answer. Oh, the exclamation mark is a convention, so it doesn't actually change anything. But functions that change the thing that you pass it to, by convention in Julia have this exclamation mark to remind you, oh, don't imagine that this is going to go inside the function and have a different namespace. I might modify it on you, so be careful.
So now when we look at y.
Yeah, exactly. So now when we look at y, now it's 7 elements. Yes, and then yes.
So given this, I'm assuming then that you can append a vectorized matrix to those genes.
So for example, you might think that you might take a too long vector and append it as the next column.
Yeah.
No, that does not work.
Vectorize Z. So that.
Oh yeah, you could list the 6 elements of this out as a vector, append something to that, and then reshape it into whatever shape you want. Well, that's kind of complicated.
Okay.
On Thursday, I'm going to talk about how to add a column to a matrix or add a row to a matrix, for example, which is usually the kind of thing that you're wanting to do to a matrix. There was a question there.
What is the fourth element?
The fourth element. And why? Here, let me. Something important that I haven't yet told you. This apostrophe sign, it flips between something being in a row and being in a column. So y apostrophe is going to take, y is a row of numbers. It's going to make it into a column. So it's just going to make it easier to look at. So now we can see the fourth. So, oh, yeah, so when, let's say that we made a vector that's 10,000 long. So that's way too much for Julia to display on the screen. So it's literally an ellipsis. That's what it is. Yes?
Can you append something at a particular index?
No, append always goes at the end.
And is there a way to insert something in the middle?
So if you wanted to insert something in the middle, what you could do is pull out the first bit. So let's say that we had z equals 1, 2, 3, 4, 5. Notice that I'm using commas instead of spaces. If I use spaces, that would produce a 1/6 matrix. Commas says this is going to be a vector. It has only one dimension. Now let's say that we wanted to insert something between the third element and the fourth element. Okay. So what we could do is pull out from 1 to 3. So this is kind of like the pedestrian answer. Part 2 is from the fourth to the end. And then we could say append something to part 1. Let's say that we append 1,000. And now let's put it all back together. And we ended up inserting. So in short, no shorthand, this kind of long-winded.
And you do all three in one step?
I don't know off the top of my head how to do all 3 in one step. So at this point, what I would do, literally, if we wanted to answer it like that, is Google, can I insert? And there's probably an answer. I want to continue encouraging you guys to ask questions and make comments during the class and outside of the class and all that. I will say that sometimes I'm thinking, oh, I want to get through this much material, so there is the possibility that I might say, I'm going to try and move on and not answer you right then. But I should be the one keeping track of the clock and how much we have to go through. You guys should never hesitate to ask questions. Okay? This is a warning that I might answer that, but never hesitate to answer. Okay. That's it. Let's go on and try and make our smoother function. So let's load up some data that I have stored in this file called pinknoise.jld. Okay. And you guys might remember that these JLD files get stored as dictionaries, where this is, some name. Usually it's the name of the variable and the value of the variable. So this particular file has both a time vector, and you guys will also remember that for dictionaries, we access the elements in the dictionary not through the number of the shelf, but through the name of the shelf. So that's what I'm doing. I'm saying put that in a variable that I'm going to call t, and we also had x, so I'm going to pull that out, and I could use any variable name, but just for convenience, I'm also using the name x, and I'm pulling that out so that I can plot one versus the other. Ooh. Man, and it's like tiny and almost impossible to see. So I'm going to set up some defaults on my plots. Let's see if this works. There we go. So up at the top of this pre-written file, there's some magic that I'm not going to explain for setting up the default font size, the line width, the line color, stuff like that. You guys can fiddle with that. We'll explain it some other time. Let's make the font size a little bigger, see if things look a little better. Okay. Maybe, hopefully you can read it a little bit more. So this is, let's say that this is some data that you got. Can you guys see it? It looks kind of tiny. I guess the answer is more or less yes. So let's say that what we wanted to do with this data is smooth it because we think that there's some noise that's corrupted the data. There's some signal in there that we might want to be able to see. So what does smoothing mean? Well, literally what we mean by smoothing is that we're going to replace each point by some local average of the points near it. And there are many ways to smooth. We're going to smooth in the simplest way, which is, for example, say, I'm going to take the 2 points before me up till 2 points after me, and I'm going to replace that point with the average of those points. So let's say that this is our vector x. And we want to produce a smooth version of x. Give it more elements. I think in that particular data file, there's 512 elements, and there's some numbers there, and if we want to produce a smooth version of x, there's going to be a vector with the same number of elements. I want it to look pretty much the same, except that, say, this one would be the average of, let's say that we said 2 elements before and 2 elements after. So this guy would be the average of these 5. Here's the corresponding element position, 2 elements before, all the way to 2 elements after. And this guy would be the average of these. Right? 2 elements before this one, up to 2 elements after. And so on and so forth, stepping through the entire vector. Let's write a function that does that. And let's write a function where we're going to give it the vector x. So it should work for any vector x. It should be able to do this. And we're also going to give it how many bins. Let's say that we call each of these elements a bin, time bin. How many in the past and in the future we want to do the smoothing of. So we might ask it to only look from 1 in the past to 1 in the future, or another time that we run it, we might ask it to look 10 in the past all the way to 10 in the future for each element. That's what we'd like it to do. So that means that I think most of the functions that we wrote up to now had 1 argument. Now we're going to write a function with 2 arguments. Looks almost identical, right? Because we want to give it the vector, the thing that we're going to smooth, and we also want to tell the function over what range we're going to smooth. So in the file, in the pre-written _day4.jl, there's a function called smoother. But let me write it out from scratch. So If we want a function to take more than one argument, it's super simple. You just separate them by commas. So, for example, let's say that we wrote a smoother function that was super trivial. All it does is reports what we got. And I'm going to press Alt-Enter to evaluate it. So now that function is defined. And whatever we pass it. So inside the function, the variable x will take the value of whatever the first parameter was. And the variable nbins is taking the value of whatever the second parameter was. Is that clear to everybody? Okay. All right. So these are the things that we want to tell smoother. And now let's do exactly what we said over here. So let's produce a vector that we could call it smoothed x. Internally, I'm going to call it y, just so that it has a shorter variable name. And that's where we're going to store the results of the average. So let's say that we're going to start it with zeros. Now, what size should y be? Should it have rows, columns? Should it be a vector? How long should it be? What do you guys think? Yes? Say again? As long as x is. How do we find out how long x is? Yeah, you could use length. Or suppose that you've forgotten. You go to Google and you type, Julia, how do I ask how long a vector is? And it'll tell you. Okay, so we want it to be as long as x is. And we're assuming that x is a vector, that x is not a matrix. So that'll give us as many zeros as we have elements of x. That's our vector y. And now what do we want to do? What could I write here? So for each element of y, I want to replace it by the average of x going from n bins in the past to n bins in the future. If I need to do this for each element of y, we probably need to loop, right? Because whatever we're going to do for this guy, we're going to do for this guy.
Wait, what does n bins represent?
So n bins is how many in the past. So for example, smoother x1, that would be look 1 in the past to 1 in the future. Whereas smoother of x comma 5 would be the same. We're looking from 5 in the past to 5 in the future. Okay. So whatever I do for this guy, for the first element of y, to figure out what the first element of y is, I'm going to do something really similar for the second element, for the third element. So what can I do here to cover all the elements of y? Tell me. I know you're thinking of it. We need some kind of loop, because there's some code that we're going to write for what to do to an element, and we're going to want to do that same thing multiple times, right? And loops are what let you do something multiple times.
Would you use a for loop?
Excellent. We could also have written a while loop, but a for loop is easy and straightforward. So what should I write? How many times do I want to do this?
As many times as x equals 1.
So say, what would I write here? For I equals 1 to what? Exactly, right? And so then whatever is in here, it will get run first with I taking on the value 1, then with I taking on the value 2, then with I taking on the value 3, and so on and so forth until I takes on the value length of x. And so it will have covered every single element from the first to the last. Yes.
Could you do it for A and Y?
Yes, you could. Then you have to pay a little bit more attention to is Y a column or a row? And so for now, I'm keeping it simple like this. But yeah, you could do that also. Yes?
What if, because you're condensing the elements in Y because it's taking the average over more than one, then why would we have Y be as long as X? Wouldn't it be shorter?
You could make it shorter. It doesn't have to be exactly. The elements of Y aren't necessarily going to be exact repeats of each other. So there's a technical sense in which you can downsample after smoothing because things are varying less rapidly. But in general, you do want as many elements. So let's do an example on the board of kind of what we're doing. Let's say that our vector x was equal to 1 to 100, 3, 1. And now let's say that we called smoother on x, looking one in the past to one in the future. So what would go in here? So the corresponding lines. So in the second element of the result, we want the average going from one in the past to one in the future. So we want the average of 1, 2, and 100. What's the average of 1, 2, and 100? Yes, 34 and a third. How did you get there? Because that pause is telling you that maybe not everybody remembers what an average is. So take us through.
We add 1 to 1 plus 3 plus 100 and divide by 3 plus 3.
Exactly. You add up all the things you got and divide by the number of things that you have. So 103 over 3 is 34. So 34. What goes in here? Yeah, so that would be 105 over 3. What goes in here? You set me off on this tangent, so I'll pick on you.
The average of 103 and 1.
And how could I write that?
104 over 3.
104 over 3. Okay, so a couple of things you'll notice. You'll notice that the numbers are not all the same, right? We're doing our smoothing, but they're not all the same. So if we want the complete representation, we do want as many elements as X had. So that's what set me off on this tangent, but I'm thinking stepping through it is probably a good idea. And the other thing that you'll notice is that I left the edges for the end because they're kind of like a special case. What do we do for this guy? We said we're going to average from one in the past to one in the future, but there is no element in the past, right? There's the very first one.
Set it like in the statement, for the first one, then we just do it.
Yeah, so there's the Julia code that we're going to write and deal with that case. And before we get to the Julia code, conceptually, we got to choose to do something. And what are you choosing to do? So literally, what are you suggesting I should write in here? The average of what?
1.
Yeah, so if I understand you correctly, what you're suggesting is normally we would have gone from one in the past to one in the future, from here to here. This guy doesn't exist. Let's just do the average of the guys that do it. So that would be the average of 1 and 2, which is 1. So what would go here? What's the average of 1 and 3? Okay, so hopefully now we've got a complete idea of what it is that we want to do with the smoother. And note that what we're doing is we're going to be stepping through all the elements in our vector. And for each of them, we're going to be picking out a chunk of elements in the vector x. This is exactly the kind of thing that we're asking you guys to do in problem 2D. All right. So we're stepping through all of them. And for each of these, we're going to write y of I is something. Does Julia have an average function, or do we have to write our own? I don't remember. So I type question mark, average. Does anything come up? Finding average doesn't exist. That means the word average isn't linked to any object. It's not the name of any shelf. It's not the name of a function. So no, it's not called average. Mean? Yeah, mean. Okay, mean. How does mean work? I could read the documentation, usually a good thing to do, or I could just try something. Mean of 1 and 2 and 5 is, yeah, 2 2/3. That's the mean of 5, 2, and 1. Okay. So it does kind of work. All right, so now that we know that we have the mean function available to us, what should I write here? I want the mean of something, but the mean of what? I don't think you and the red sweater have yet said anything, so I'm going to pick on you.
Want the mean of x at the position in I, from the position at I minus bins to the position of x at I plus bins.
Exactly. And if you guys remember this colon notation says start at the element number I minus n bins, go in steps of 1 until the element I plus n bins. This is exactly what you said, right? Is that clear to everybody? So if we step through all of these, that should do it. And then we return y, that's the answer.
Just stored in.
You have to account for the two cases.
The edge cases. We've forgotten the edge cases, right? So I don't know how many times I've written a function like this. Usually I write it, I run it, I get an error. I forgot the edge cases. So what shall we do with the edge cases? These are special cases. We need to kind of look out for them. What could we write to deal with those?
If statement, you can specify.
We could do an if statement.
I is equal to 1 or I is equal to 4.
Yeah, so we could say if I is equal to 1. However, what if, let's say that n bins is 10. And the special cases, there's going to be a bunch of special cases, right? Because this guy will be a special case, this guy will be a special case, this guy will be a special case. For example, this third guy, we'd be looking at 3 minus 10 from the minus 7th over here, from the minus 7th to the 0th that don't exist. So we get a bunch of special cases. So I'm going to do something else. I'm going to explicitly write out where I want to start, and where I want to end. So if I write things like this, so far nothing has changed, right? At least I hope it seems to you guys that nothing has changed. All I did was explicitly write out a variable that says what's the index at which we're going to start, and what's the index at which we're going to end. And now let's do the special cases with these variables. What are for start point, what are the conditions on start point that are a problem?
Start point is less than 1.
Exactly. So what should I write here?
Okay, start point is less than 1.
And if start point is less than 1, what do I want to do to it? How do I want to adjust it? So let's think of a special case. Let's say that I equals 2, so we're looking at this guy, and let's say that n bins is 3. Okay. So that means that start point I minus n bins would be minus 1. But from where do we want to start? Our averaging, where do we actually want it to start? At 1, at the first element. So let's say that if start point is less than 1, bump it up to 1. And how about end point? What are the conditions on end point being a problem? Yes?
If it's greater than the in of
And what do we want to adjust it to if that's true? The length of x. So I think this is looking pretty good. I think I wrote it in a more crummy way in your file, but basically the same thing. Let's see if it works. So I press Alt-Enter to copy-paste all this into this file. Now we have our smoother function. So say we could run it on our data. Our data, just to remember, was this vector x. So we could run smooth. We could plot, say, t and the smoother of x. How many bins would you guys like to smooth it by? Give me a number. 10. Why not? It didn't crash. Is it correct? It eyeballs kind of okay. Much better, you write a little piece of code, you test it with something really simple where you know what the answer is. We already figured one out, right? We've got this example where we know exactly what the answer should be. Let's see if it does that. So when you're writing code, when you're writing big chunks of code, you want to break the problem down into little chunks, write a function for the little chunk, test that little chunk so that you're totally confident that your function works. And then once you've tested that, go on to the next step of the problem. And that means, running it on X is great, but it's not so great for, say, in what you see on the screen, were the edge effects, did we get the edge effects right? I can't tell with that big vector X with 512 elements, right? So let's use a smaller one where we can tell exactly what's going on. So let's say that we did the smoother of X. Our vector was 1, 2, 100, 3, 1, and we wanted to smooth from -1 to +1. What do we get? It's in a row, so we get these darn ellipses. Okay, let's put the apostrophe so it will make it in a column and display it as a column. Here we go. 1.5, 34 and a third. 105 over 3 is that 35? Yeah. 104 over 3 is that 34 and 2/3? Yeah. And 2. Okay, so it looks like we're getting the edge effects. It's doing what we wanted. Cool. Okay, so let's go back to plotting, t versus the smoother of x at, did you say 10 bins? I thought you said 10 bins. I guess I must have written that before. Cute thing to do might be to compare the smoothed version to the original data. So we can do that by plotting something on top of this. So the exclamation mark, remember when we were doing append, said modify what you're calling. In this case, here it means modify the existing plot. Don't erase it, modify it, in this case add something to it. So let's plot the original data, and let's plot it in a different color so we can see both of them. So red is the original data, and green is the smooth version. Yeah, I'm willing to believe that. And let's say that we smoothed much less. We only did 2. It's following the jaggies much more closely. Let's say that we smoothed much more. Let's say by 100. Now it's like super smooth. You might say, oh, that's so smooth that it's not following what I'm interested in the data. Now I'm just having fun, and I should stop. But once you've got a function that plots things on the screen, it's always fun to fiddle with the numbers and see what it looks like and do stuff like that. Okay, I am very happy because we seem to have covered smoother, which was the main thing I wanted to make sure to go over. I don't see any horribly furrowed brows, but this is a great opportunity to ask a question if there was anything in that wasn't clear. Yes?
This is probably something I can Google, but is there like a plot clear type thing so you can erase the plot before you plot it?
There is. I've forgotten what it is, and so you can always do that. Yes?
How would you clear out your workspace and all the variables?
Oh, there's actually not a great way to do that. Um, so yeah, so if you type this workspace, it stashes your workspace in a different store, and it opens up a new one. So functionally, from your standpoint, it'll be as if you cleared your workspace. It takes up a little bit of memory. It's not really that important. So this will work fine. So if you do workspace, how much was T? Whoa, it's still there. Okay, I take that back. I've forgotten. I don't know how to do it.
Just for like testing out concepts and stuff. Right, like that.
Okay.
Exterior session.
Yeah, you could start a new session. I don't know. I'll go find out, or all you guys could Google it, post the answer on Piazza, and then we'll find out. Yes?
For vectors, we can determine how long they are by just length, but in a matrices, if we do like
Great
row
question.
length versus column length.
Great question. Say that you have a matrix, and you want to ask how many rows and columns does it have? Length doesn't cover it, right? Because actually, you can ask for the length of a matrix, and then it tells you the total number of elements it has. Right? But if you want to know the number of rows and columns, you call size. And size returns the number of rows and the number of columns.
Okay. Can you use that like to specify like you want to use size of Y, but you only want to use the columns and you want to use right then?
So suppose you only want the columns.
Yeah.
Okay? You can pull those out by saying, oh, give me the first element of your response. And if you only want the rows, you say, give me the second element. Sorry, it gives you first the number of rows and then the number of columns. It's rows then columns. Sorry about that. Okay. So the second one is the number of columns. And this actually covers something that I wanted to point out, which is that functions don't have to return just one thing. They can return more than one thing. And when they do return more than one thing, they return it in this form. It kind of looks like a vector. It doesn't have square brackets. It's got these parentheses. It's called a tuple. And that means that it's a vector, a constant vector. You can't modify its contents. It's the answer of something. But for all intents and purposes, the way you access it is the same way you would access a vector, asking for the first element or the second element or whatever you need out of that. Okay. So any other questions about smoother? For loop that we wrote in there. No? Excellent. Okay. So then what I want to do is see whether we can go back to that thing that we started last week, finding spikes, and then we're going to bin them and we're going to plot them all. So I think the next step, here it is. So we've covered, something very important that I haven't mentioned, but kind of like that inexact error, this is often an error that can come up, which is when you pass a vector to a Julia function, Julia doesn't bother making a copy of the vector, which means that if you change the contents of the vector, if Julia had made a copy, you could change the contents inside the function, and it wouldn't affect the vector outside the function. But for speed, Julia says, you know what, I'm not going to copy it, and that means I'm just going to pass a pointer to that vector. So a pointer to where its shelves are. So that means that if you modify the contents of the vector, it'll get modified outside the function as well. So let me just show you an example of that. So say that you had this vector, y. Okay. So here's our vector y. And now let's say that we wrote this function, example 0, which modifies the contents of the vector. This is different to if it were just a scalar function. If it were just a scalar function, you modify it inside the function. You're not modifying the variable outside the function. But now let's call example 0. So let me show you y again. Here's y, 1, 2, 3, 4. Let's call example 0 on y. And notice we didn't put an exclamation mark or anything here, so there's no warning to the user that we might be mucking with y. Okay. And if we now ask what y is, we've modified the contents. So that's a common source of confusion. Because it might modify contents without you thinking that it was going to do that, and then you're tracing out that bug and you get confused. So what do if you don't want it to modify the contents? Well, the first thing you do is, since Julia doesn't by default copy the vector for you, you ask it to do that. You say, don't do the default thing of passing by reference, copy the vector. So here's the same function, example 0, where the first thing we do is just copy the original vector, and now this variable vec here doesn't refer to the contents of this vector y, it refers to the copy. We can muck about with its contents, and everything will be fine. So let's do that. And if we now run, so let's say that we set y back to 1, 2, 3, 4. If we run example 0b, we haven't changed the contents of y. So just watch out for that. If you're modifying the contents of a vector inside a function, be aware that you're going to modify the vector outside the function. If you don't want that to happen, make sure you copy it first. Okay. So we've gone through smoother.
Oh, I have a question.
Yeah.
So if you didn't put the copy and you just said that effect is equal to y, how does that affect?
Same thing. So in fact, functionally what Julia does here is say vec equals to y. It's exactly the same as having written that. So implicitly when you call the function, that's what it does. So what does it really do? Say that y is this set of shelves. What y actually is a pointer in memory to where the shelves start. So when it copies that, when you write vec equals y, what it's copying is the pointer, the arrow that says my elements start here.
Oh,
So
so
it
if you
points to the
modify
same-
y, then effect is y.
Yeah, so vec equals y is not enough. And in fact, we can do that out here. So for example, here's our y. And now let's say a equals y. And now let's modify the second one. And we also modified it in y. So when modifying vectors, just be careful about that. Okay, where are we? So we already did the smoother. And last week we did the peak finder. Right? Do people want me to go over the peak finding function again? I'm kind of hoping that we'll write new ones, but if it wasn't clear last week, that is something that we can do. Any votes for going over the peak finder function? Okay, last chance. All right, so the peak finding function, you guys will remember, would find all the peaks. Let's say that we have this vector, and let's say that we plot it. Plot asks for, if it's going to plot everything in one line, it wants it in a column, so that's why I'm putting the apostrophe. Whoa. Oh, when I did the workspace thing, it did kind of get rid of that. So, sorry, that was a little too fast. I called the function plots, and Julia said, I don't know what plots you're talking about. So that told me, oh, I need to do this. That's what says use the package plots, which includes the function plot, and so that's why I wrote that. Okay. So let's plot x on the screen. The first time you call a function, Julia recompiles the last little bit, so it takes a little longer. Now it's taking way too long. And it didn't even do anything. Okay, I don't know what I did with my workspace. I'm just going to start it completely. So here's our x, and this time I made it into a row, so hopefully now it will plot. Here we go. Okay, so there's x. So let's run the peak finder. Oh, hang on one thing. I do want my default sizes and all that, so it's a little bit more legible. Okay. So there's x, and we wanted to find the peaks in x. So where are the peaks in x? There, at the third element and the seventh element are both peaks in that little mountain range. So let's see what peak finder of x says. Oh, I haven't. Oh, by exiting, I may now be in the wrong directory. Yes, I am in the wrong directory. So I moved to the right directory. Now I can include the file that I want. And that defines this function peak finder. It also does a bunch of other things that we haven't gotten to yet. But now we do have peak finder defined. And peak finder, this is what we wrote last week. It's working. It says the third element is a peak, the seventh element is a peak. But we wanted to run this on data that was actual membrane voltages from spikes, right? And that data came from this file. Let me load it. And this data has a time vector and a capital V matrix. So let's again pull those out. So what is this? Oops, sorry, I should have written that with a square bracket like that. And this capital V matrix has 5001 time points. And those correspond to the length of t. And it has 50 columns, and each one of those corresponds to a different neuron. So we could plot, say if we want to plot the first neuron, we would plot it like this. And so here we are. And so you guys will remember the problem that we were facing last time. We want to find those spikes. If we find the peaks, that's not going to be enough because there's going to be lots of little local peaks just due to noise. We wanted to find peaks that were also, where the membrane voltage was also bigger than, say, -20. So let's write that. And having found our peaks, having our peak finder function, that's a building block that we can now use to write the spike finder function. So let's write a function spike finder. And what we want this to do is return the times of the spikes. And what we're going to give it is a time vector, right? Because we're going to find where the peaks are, and the corresponding element in the t vector, that's the time in milliseconds, right? Time is the t vector is the one that's keeping track of, are we measuring things in seconds, milliseconds, hours, whatever it is. So we're going to give it the time vector, and we're going to give it, here I'm going to call it volt, just to not confuse it with the big V matrix. The big V matrix is multiple neurons. Let's write this for just one neuron. So say volt might be a vector that looks like this. The voltage is a function of time. And so now what we want to do is find all the peaks. Ask, for each peak, ask, is the voltage bigger than -20? If it is, that's a time, that's a spike time. So how do we do that? First thing to do is find all the peaks. How do we find all the peaks in our volt vector? Yeah, we just wrote it, right? We just wrote that function to help us write this. Thank you. So first thing we do is find the peaks. No, it doesn't have to be stored in the same folder. So when we run include, or we do that alt-enter so that it does a copy-paste, it runs the lines that define the function through the console, through what they call the REPL. And then once you've defined the function, that function exists in your workspace.
Oh, so even if you open up a new window, right?
Even if you open up a new window, a new file. So functions are a little bit like variables. A variable is used to define where you store numbers or strings or whatever. A function is also a pointer to this set of code. And once you define it, the same way that a variable keeps on existing, exactly the same. So yes, so peak finders is still with us. Okay, so we found all the peaks, and now for each of these, we want to ask, is the corresponding voltage bigger than minus 20? So how would I write that? So we said we want to ask, for each of these peaks, we want to ask whether it's bigger than minus 20. So that suggests that we want to write a for loop, right? Because we want to loop over each of the elements here. So let me write it out on the board a little bit. We're going to run peaks. Okay? And what was the peak finder? Let's say that so here's x, and here's peak finder of x, and let me put an apostrophe so it all comes out horizontally and we can see it on the screen. Right. So if this vector was our series of voltages, was our volt vector, then when we run peak finder, we're going to come out with something that is going to look like this. It's going to be a too long vector. It's going to have as many elements as there are peaks. And it contains the indices of where the peaks are. So this was for this vector 1, 2, 5, 4, 3, 3. So that said, the third element is a peak, the seventh element is a peak. So now for each of these, we want to ask, is the voltage bigger than minus 20? So how do I write a loop that will loop over each of the elements of peaks? Yes?
For I equals 1 to the
Exactly. Very similar to what we did in the smoother function, right? So for I equals 1 to length of peaks. And just to emphasize that the variable that we use here doesn't always have to be called I, let's this time call it K. Because it can be whatever you guys want. Okay, and for each of these, what do we want to do?
You want to access that index in X. So, and then check if it's greater than X.
Yeah, so what's the value of the voltage? So here, peaks of I, so let's say that we're running through the loop. Let's run through the loop mentally. The first time that we run through the loop, I is going to be equal to 1, so it's going to point to the first peak. And peaks of I is 3. And what's the value of x at that index? 5. So to pull out the value of x at that index, what we want to write is x of peaks of I. Right? So it's getting a little nested, but bear with me, right? This is I is telling us which index of peaks, and peaks is a list of indices itself, indices of x. So x of peaks of I says when I is 1, x of peaks of 1 is the same as x of 3.
Do you need K?
Sorry, say that again?
Do you need K? Substitute there.
Oh, thank you.
And also
Yes.
volt instead of X.
And also volt instead of x. Thank you. And what do we want to ask about this voltage?
Is it greater than negative?
Is it greater than negative 20? So if it's greater than negative 20, what do we want to do? Store it. Okay, so let's make our list of spike times. Let's say our spike times is going to be zeros. I'm going to give it only one dimension, right? Zero. It's not going to be, our list of spike times isn't going to be a matrix with rows and columns. It's just a list. And I'm also saying, oh, I want it to be 0 elements long. Kind of a peculiar thing, but that does work. It says, I'm making a list. It doesn't have anything in it yet. Right? So far, it's empty. Okay. And so if we found something that we want to put in that list, let's append it into that list. So we might write something like, what should I write here? What do I want to append? I'm going to pick on somebody. Yes?
You append S times.
Right? This is who we want to append to. That's the list that we're going to be adding another element to. And what do we want to append?
The value in X at that index.
The value in X at that index. So let's put volt of peaks of K. Okay. And after we've run over all of the peaks, we've checked all of them, we've appended our list. At the end, we want to return the list. Okay?
Don't we have to add the time and not the voltage?
Yes, I was going to run it, and we were going to see the mistake. Yeah, so we know that volt of peaks of I, that's the value of the voltage, right? But we were trying to find the times of the spikes. So where do we find that information? Where's the information about times? Yeah, the vector t was as long as the vector volt. So remember when we did the plotting, so let's say that volt equals EF 1, right? And when we did the plotting, right, this tells us that these two vectors are the same length, and each element of volt has a corresponding element of t that here is the time at which that voltage occurred. Does that make sense? Kind of. Yeah? Oh, yes. So what would we write here? What would we do here? Any suggestions? So remember, we're looking for volt, however many long volt is. So let's say this is volt. And let's say t is going to be the same length. Okay. And let's say that t ran in 0.1 milliseconds, so the t is going to look like this. So if the first peak is at the third element of volt, which element of t is telling me the time at which this value happens? The third element, right? There's a one-to-one correspondence. So when did this value happen? At this time. When did this value happen? At this time. So this is the third element. The third element of t tells me the time at which we got that. So we should write t of peaks of k. And now I think it's going to work. Let's see if it works. I'm not sure. So I've saved the file. Let's include it. We could include it, or we could also do the Alt-Enter thing. That's kind of like a copy-paste. Totally same thing. The only difference is if you want to run the debugger, you need to do include. So, okay, it accepted the file. We didn't make any syntax errors. Let's now run it. Spike finder of t volt, and volt is this thing up here. Let me do the apostrophe so you see the. Okay. Same thing as when we did the smoothing, right? I'm running it on something that's a little bit too complicated for me to actually evaluate whether it's working. Let's run it on something simpler. How about running it on this example, right? Where we know exactly what should happen. So now let's say volt is 125432291 43291. And actually I want to make it a vector, so I should separate it with commas so we don't get confused with like rows and columns. And let's say that our t is exactly that. 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. Did we get it right? Let's plot one against the other. Yep, there it is. Okay, let's ask when the spike times are. Spike finder of t volt. Really? Oh, thank you. Exactly. Remember, we were looking for peaks that were bigger than, where the value of the voltage was bigger than minus 20. All of these peaks are bigger than minus 20. So let's change our example. Oops. Let's change our example to something that looks like, or actually, what we could do is change this to say you have to be bigger than 8. So we're looking for peaks where the value of the voltage is bigger than 8. If we find one, we put that in our list of times. Yes?
Could you make some kind of variable, say, like limit or something, and then have it be if volts, and like add that in the beginning with spec finder, and have it be the volt, the record peak of K is more than limit?
Yes. So let's do that in a second. For now, let's see whether this code works. And I've got 2 minutes more. So of these peaks, which one is bigger than 8? Only the second one, right? The other one is less than 8. So this should return 0.7. So let's include that. And now let's run it. Okay. And it returns only this one. So sometimes you might want to change the threshold. Sometimes you want to change your definition of where it is, right? So let's make this a variable. And what you could do, and bear with me for 2 minutes, is put it here, so pass it as another parameter. And I'm going to tell you guys one last thing, which is explained in the file that we sent out. Let's write it like this. And this is a special notation that can be very useful that makes this an optional parameter. So what this means is, sorry, let's include it so that now we define it like this. This means that it has a default value. If you don't specify it, internally in the function, threshold is going to take the value minus 20. So we could run spike finder. We could run spike finder t volt. And now it's running with the threshold at minus 20. Anything above minus 20 works. You can choose, it's optional, you can choose to add it in this manner. It has a name, and then you say, I want this variable, which is named, that's why it goes after the semicolon. I want it to take on this value, say 8. And now it runs with threshold having that value. And sometimes you want many arguments, and it's easy to forget which ones are which. And so having these named arguments can be very convenient, and also giving them defaults so that you don't always have to call a function specifying everything. I'm going to do one last example. What if we say the threshold is 1,000? Well, none of our voltages reached 1,000, so that should find nothing. Yeah. Oh, that was a question. All right. It is 2:50. Thanks, guys. Keep the comments coming.
Why do we need to transpose?
Give me just a second to try and stop the recording.
Okay.
Which